Now from the graphing, for these next couple of days, we are going back to systems of equations to solve, so getting away from systems of inequalities completely here. But now our equations have 3 variables, meaning we have 3 equations in our system. So however many variables you have, that's the number of equations you have to have in your system in order to solve it. So I do also want to mention the front page, I am explaining what these solutions mean graphically, but we are not actually graphing them. So you want to be able to solve a system of linear equations that has 3 variables, and like systems of equations in 2 variables, these systems can have 1 solution, infinitely many solutions, or no solution. If your system has 1 solution, it will be an ordered triple. So ordered pair is when you just have 2 variables, x and y. If you have x, y, and z, it's an ordered triple. And the graph of an equation that has 3 variables has to be graphed in a 3-dimensional plane. So 3 variables represents 3 dimensions. And so a graph or an equation would be in the shape of a plane. It's not just a line, it's a plane. Again, we're not graphing these. But the graphs of a system of equations in 3 variables form a system of 3 planes. So this is what it means graphically depending on the solution you get. If you get 1 solution, it means all 3 planes intersect at exactly 1 specific point, and that's your ordered triple x, y, z. If you find in your system that you get infinitely many solutions, it could mean one of 2 scenarios. And I'll explain what this looks like algebraically because we're not graphing them. So it either means that all 3 planes will intersect in a line, and there's infinitely many points on a line, so infinite solutions. Or it could mean that all 3 planes are the same plane, so they're intersecting at every point on the plane, which again, there's infinitely many. And then if there's no solution, what I want to point out here, and again, we'll talk about this algebraically, it means there's no points in common with all 3 planes. So you still might have points in common with 2 of your planes, but not with all 3. Your stuff is just on that chair, Molly. So notice there's different graphical representations there. 2 of your planes could intersect, but it's just not that all 3 are going to intersect with each other. It could be that none of the planes intersect. So ultimately, we are not solving these by graphing. We are solving them using the same methods we did use, the algebraic methods for systems of 2 equations. So we're using substitution and elimination. However, it's just more of a process because you have 3 variables to find. So I have it broken down into kind of the steps that will follow. So if we go on to look at example 1, it is important here. It's not, and don't look at this and think every problem you do is going to take up a whole page. That's not it. I just wanted to leave enough room here to explain it. But it is important when you are working through these that you keep all of your work organized. I mean, that's always important, but because there's multiple steps to these, you really want to be able to follow your own work as you're going through it. So here's our system of 3 equations. And I will typically kind of label these equations. That's up to if you want to do it, but that way I do it mainly when I'm showing all of you how to solve these. So when I'm referencing different equations, you know which ones I'm talking about. So step 1 is to eliminate one of your variables, either x, y, or z, by using 2 pairs of equations. Okay, so in step 1, what I'm going to show you is I'm going to pick 1 pair of equations. So I'm going to pick equations 1 and 2. And I'm just going to copy those down. You don't always have to start with equations 1 and 2. That's just what I'm choosing here. And with these 2 equations, I need to pick a variable to eliminate. So I'm going to use that elimination method where I may have to multiply one or both of my equations by something to eliminate that variable. But you can pick any of the 3 variables. You just have to eliminate it. So what's a variable that we could eliminate here? Or that would be easier to eliminate? Okay, y. That's just the one I heard more clearly. So if I choose to eliminate the y, what do I have to do with my system to get the y to eliminate? Multiply by 3 or negative 3. I would choose the negative 3 so that I can add the equations together. They're opposites that way. So multiply the entire bottom equation by negative 3. So my top equation, I'm just going to rewrite. Bottom equation now will become negative 6x minus 3y plus 3z equals negative 15. And now that I have done that to the second equation, then I can add my equations together, and I have positive 3y minus 3y. My y's will eliminate. And I can add the rest of my like terms, so 5x plus negative 6x is negative x, or negative 1x, plus 2z plus 3z is 5z, equals 2 plus negative 15 is negative 13 plus 0. Okay, so I eliminated y. I still have an equation, though, that has x and z, and I'm just going to keep this kind of off to the side. That's going to be part of my step 2, but I don't need it anymore at this moment, but I need to kind of keep track of where that is. So now, notice it says eliminate one variable by using 2 pairs of equations. So now I have to do this process again, but with a different pair of equations. So I didn't use equation 3 the first time, meaning I have to use equation 3, and I pair that with either equation 1 or 2. When I do this, I have to eliminate the same variable. So I eliminated y the first time, I have to eliminate y again. So I'm actually going to pick equations 2 and 3 instead of 1 and 3, because if I pick 2 and 3, it's going to be easier to eliminate the y. All right, and if I have to eliminate y again, I don't have a choice this time, I would need to multiply my top equation by negative 4 so that it cancels out with the positive 4y. So that means my top equation will become negative 8x minus 4y plus 4z equals negative 20. My bottom equation stays the same. And I can eliminate the y's by adding the equations together. Negative 4y, positive 4y cancels out. Adding everything else, I get negative 8x plus x would be negative 7x. 4z plus 2z would be plus 6z. And then equals negative 20 plus 16 is negative 4. And I get another equation that doesn't have a y, but does have an x and a z. So by doing this, what happens is now if I take these 2 equations that I got as my result and I put those 2 equations together, they form a system of 2 equations. Because I only have 2 variables now, x and z. And that's why it doesn't work if you eliminate a different variable each time, then your 2 equations wouldn't have the same variables left over. So now this is where we take these 2 equations and put them together in step 2, and we solve that system of 2 equations so that we're able to find the values of x and z. So I'm just going to rewrite these 2 equations. And you can solve this system using substitution or elimination, whichever you prefer. Say we decide to use elimination. It's set up a little bit easier for elimination. What variable would be easiest to eliminate first? The x, and I can do that by multiplying that top equation by negative 7 so that it becomes positive 7x. So then if I multiply everything in the top equation by negative 7, I'll have positive 7x minus 35z equals negative 7 times negative 13, positive 91. And then my bottom equation is staying the same. And now if I add these two equations together, my 7x and negative 7x eliminate. I have negative 35z plus 6z, so that would be negative 29z. And then 91 plus negative 4 is 87. And now I can find what z is equal to. So I can divide by negative 29, and z will equal, I believe it's negative 3. 87 divided by negative 29. Okay, negative 3. So we have one of our three variables. Ultimately, we're trying to find what is x, what is y, what is z. I have one of the three. Now that I know what z is, how can I find x? Yep, plug z into one of these two. I would say one of the two original. Let's just say I pick the top one. I'll have negative x plus 5 times negative 3 is a negative 15 equals negative 13. And then to solve for x, I'd want to add the 15 to each side. So negative x is equal to positive 2, meaning that if I divide each side by a negative 1, x is equal to a negative 2. Okay, so now I'm closer. I have 2 of my 3. So now the very last step, the third step, is to take the 2 values you have and substitute them into one of your original 3 equations to find your third variable, which in this case is y. So looking at the top 3 equations, let's just say I plug it into the second one, the 2x plus y minus z equals 5. It doesn't matter which one you choose. That one just looks the easiest to me. So if I replace the x with negative 2 and the z with negative 3, I'll get 2 times x is negative 2, so that's negative 4, plus y. And then I have minus z, which would be minus negative 3, so that'll change to plus 3, equals 5. And then combine like terms on the left, negative 4 plus 3 would be a negative 1, so negative 1 plus y equals 5. Add 1 to each side, and I get my y value is positive 6. And then make sure I have the 3 values. I just circled them because you have a lot of work going on. I want to keep track of what my values are. Your answer, though, should be an ordered triple. So in x, y, z, I have x is negative 2, y is 6, z is negative 3, and that ordered triple is my answer, meaning these 3 planes would all intersect at one specific point. Graphically, that's what your solution would mean, even though we're not graphing on it. Questions on that example? Okay. Yes, it's a lot of steps. You just have to really make sure that you're paying attention to what steps you're doing where, keep track of your work, you're using the right pieces of information. You can check your answers by substituting these 3 variables into your 3 original equations. Make sure they all work. Again, I'm not requiring you to show me that you're checking, but know that that's an option for you, and then you know if it's right or it's wrong. Check it into all 3, make sure that it does work. Okay, we will go on then to example 2. In examples 2 and 3, some different things happen. Okay, so we'll go through these ones together as well. So if I look at example 2, if it helps to label your equations 1, 2, and 3, by all means do that. So again, first step, you have to choose 2 of your equations. You're trying to take 2 pairs of equations, eliminate the same variable. So say I picked equations 1 and 2. So I have 3x minus y minus 2z equals 4, and 9x minus 3y minus 6z equals 12. And what's a variable that looks easy to eliminate? The y's. Okay, if I want to eliminate y, what do I have to multiply the top equation by? 3, or I'd say negative 3. Since the bottom one has a negative 3y, I'd want this one to be a positive 3y. So multiplying everything in the top equation by negative 3 would get me negative 9x plus 3y plus 6z equals negative 12. And then my bottom equation is staying the same. And what happens? Everything cancels out, so I get 0 equals 0. Okay, what did this mean when we had systems of 2 equations? You got 0 equals 0. It meant infinitely many. Now, in systems of 3 equations, this could mean the same thing. This tells you right off the bat that you have 2 choices for your answers. It's either infinitely many or it's no solution. But you can't stop at this point and say, oh, it's infinitely many. It might be. It still could be no solution. Ultimately, what this tells you is that these 2 equations, equations 1 and 2, represent the same plane. Now, would you necessarily have to tell me this on a quiz? No, but I want you to understand what that 0 equals 0 means. It means those 2 planes are the exact same plane. You still have to check, though, does that plane intersect the third one? If it does, there's infinitely many solutions. If it doesn't, there's no solution. Because these 2 planes could intersect, but maybe they don't intersect with the third one. And you want solutions, you want all 3 planes to intersect somewhere. So I still have to do the second part of that step 1 and pick another pair of equations and see what I get there. So let's say I picked, I don't know, it's probably going to be easier if I'm looking to eliminate a variable. It's probably going to be easier to pick 1 and 3 to try to eliminate. And now, even though I picked y the first time, that doesn't mean now that I have to pick y the second time, because everything canceled out the first time. So picking y again isn't necessary. I suppose I could. Let's say if I did pick y the second time, we'll just go with that. I'd have to multiply the top equation by a negative 2. So that would make my top equation now negative 6x plus 2y plus 4z equals negative 8. My bottom equation stays the same. And now with this pair of equations, everything on the left side cancels, so I get 0. On the right side, though, that doesn't cancel. Negative 8 plus 11 is 3. What does this mean? That's no solution because it's a false equation. 0 doesn't equal 3. So this tells me that while these 2 planes represent the same plane, this tells me they don't intersect with the third plane, so there's no solution. Or if you wanted to make the empty set symbol, that's perfectly acceptable for no solution. If I would have picked equations 1 and 3 first and got 0 equals 3, anytime you get a false solution, even if it's your very first step or a false equation, it's automatically no solution. So at any point in a problem, if you get this, it's no solution. I'm just showing you if you get 0 equals 0 in the very first step, you have to do a second step. You can't base your answer off of that first step. Okay, any questions on example 2? Okay, so then in example 3, so this one also works out a little bit differently if we start out the same way. So I'm trying to pick 2 pairs of equations, eliminate a variable. Somebody give me a pair of equations to use. Just 1 and 2. I typically start with 1 and 2. You don't have to. It's easy. All right, and a variable to eliminate. Y. So multiply the top equation by -3. So negative 6x minus 3y plus 9z equals -15. And the bottom equation stays the same. Well, what happens here? Everything on both sides cancels out, 0 equals 0. Okay, again, cannot base our answer on that. We have to do a second step. So pick another pair of equations. 2 and 3. So all right, and I would argue, so again, I don't have to pick y this time because I got 0 equals 0, and I would argue picking y wouldn't be the easiest here anyway. I would pick x to eliminate and multiply the bottom equation by -6. So my top equation is staying the same. Bottom equation is -6x minus 12y plus 24z equals -42. Okay, so x does eliminate, but nothing else does. So now I have 3y plus a -12y, so that's -9y. -9z plus 24z is 15. So plus 15z, 15 and -42. Okay, I am at a point where I can still say what my answer is, even though I got this. The answer is infinitely many solutions. Or if you just put infinite solutions, it's fine, just don't put the infinity symbol. So this is why it's infinitely many. Again, anytime you get 0 equals 0 in the first step, it's either infinitely many or no solution. So this tells me my first 2 equations were the same plane because I got 0 equals 0. And then because I'm getting an equation here, this tells me that my 3 equations intersect in a line. That's what this tells me. If I got 0 equals 0 again, they would be all the same plane. But regardless, if you get 0 equals 0 and then 0 equals 0 again, or an equation, it's infinitely many. If you get 0 equals 0 and then a false equation, it's no solution. So just understanding that I got to this step, I can stop, I'm good.